you very much for the introduction. Also, thank you for inviting me. It's a really exciting conference. I'm sorry that I could not attend yesterday and before yesterday. I had to examine my poor students yesterday, so I can only attend today. So I'm going to talk about the use of multi-level models for performing meta-analysis. So my talk will consist of several parts. First, I will introduce multi-level analysis. Afterwards, I will talk about how you can consider meta-analysis as a specific case of multi-level analysis. Afterwards, I will talk about some opportunities when you use the multi-level modeling framework for analyzing raw data over studies or for analyzing effect sizes. Afterwards, I will say something about when and how multi-level models were used for performing meta-analysis, and finally I want to give some ideas, some reflections on how you can present the results of multi-level meta-analysis. So first, short introduction in multi-level analysis, and I will use an example, data collected in Flanders, in the Flemish part of Belgium, longitudinal study in which more than 6,000 students were measured 5 measurement occasions during their secondary education. More than 6,000 students coming from 57 schools. And so here, for instance, you can see part of the data. So on the x-axis, you can see the performance of the students on an exam of mathematics in the beginning of secondary education. On the y-axis, you can see the performance of the students on the mathematics exam at the end of the second year of secondary education. And of course, you can see a positive linear relationship that can be described using a regression equation that can also be used to make predictions. But there is a problem with this kind of analysis and this kind of data sets. The problem is that here students are nested within schools. So you have several students coming from the same school, and this can make that residuals are not independent, whereas this is an assumption in ordinary regression analysis. What does it mean? Well, suppose there is a school that is performing very good. So in the sense that teaching is very good, and this makes that students are performing better than you would expect at the end of the second year, than you would expect based on their score in the beginning of secondary education. Or there may be a school that is not doing such a good job, and then you can see that the scores of these students are lower than you would expect. So you can see now that the residuals are not independent. If a new student is saying, well, I'm from school 2, you can already expect that for this student, you also will have a positive residual. So in other words, the positive residuals of the students of that school 2 will give information on the residual of that new student. So residuals are not independent. Why is this a problem? Well, if residuals, or if students are nested within schools, and if there are differences between schools, then this means that there is some overlap of information. Students are to a certain extent copies of other students from the same school. So there is overlap in information, and if we do not take this into account, then we are overestimating the total amount of information we have, and from a statistical point of view, this is reflected in 2 small standard errors. And if we use these standard errors to perform statistical significance tests, this will make that the type 1 error rate is not under control, that we make too many type 1 errors. So if a null hypothesis is correct, we will too easily reject this null hypothesis. What can be the solution? Well, we could do separate regression analysis for each school, but remember in this data set we had 57 schools, so this would mean that we have to do 57 separate regression analysis. This could be a solution, as you see in this graph, because now the residuals are independent. For each school, now you have positive residuals as well as negative residuals. So residuals do not give information anymore on the residual of a new student. But this is not, here you can see the separate regression equations for each of the capital J schools, but this is not a very efficient way. We have to do 57 analysis, and maybe for some schools we only have data from a few students, which means that parameter estimates will be not very reliable. Also, in this way, we cannot study to what extent there are differences between schools. An alternative is that we use school dummy variables in our regression analysis. Then we can do one regression analysis, but you will have a lot of coefficients. So here, for instance, we have a dummy variable for school 2, dummy variable for school 3, and until school 57. So this would mean that we have, instead of one intercept, we have 57 coefficients, and instead of one regression weight for our x variable, we will again have 57 coefficients. So we have 2 times 57 regression coefficients, which is, of course, not very efficient. How can we solve this? Well, a multi-level analysis can be a solution. So the idea is, well, we start from an equation, the equation that I showed before, but now I added an index j, referring to the school. Also, the intercept and regression weight of x gets an index j, which means these coefficients can vary over schools. And this variation is described with additional equations. So the first equation is describing the variation within schools. These equations are describing the variation over schools. So what does it mean? So the weight, the regression weight of x depends on the school. And here we say, well, it is equal to an overall slope plus a random residual that is typical to the school. And so what is nice about multi-level models is that we do not have to estimate all these betas. We do not have to estimate regression coefficients for each school separately. We simply estimate the mean intercept, the mean slope, as well as the variances and the covariance. I did this analysis for the example. You get very similar regression coefficients here, but now this analysis takes into account when testing these parameters that students are nested within schools. So standard errors will be larger. You can also get also information about the variation between schools in the intercept and in the slope. Also covariation, so a positive covariation means that if for a specific school the intercept is higher, you would also expect that for that school the slope is higher. Afterwards, if you want, you can also estimate the individual betas. And so based on these estimates, I composed this graph. So for each school, you can see a blue regression line, and the red line refers to the mean intercept and the mean slope over all schools. Of course, if there is variation between schools in intercept and in slope, it can be interesting to try to explain why there is variation. So maybe we can include characteristics, school characteristics, in these equations at the second level. For instance, in the example, I included a dummy variable indicating whether this school is a private school rather than a public school, and these are the results. So for public schools, the intercept is 13.73. For private schools, the intercept is 1.12 points lower. Yeah, so 13.73 minus 1.12. The slope for private schools is slightly higher than for public schools. Okay? This is illustrated in this graph. So we have an interaction effect. This term, in fact, is an interaction term. It's cross-level interaction between the mathematics 0 and the type of school. So in this example, we had a two-level structure. So we have students nested within schools, but of course this structure can also be recognized if we have repeated measures. If we have repeated measures, then again we have two levels, and at both levels there can be variation. So we have at the second level subjects, and within subjects we have repeated measurements. There can be variation between measurements within subjects, can be variation between subjects, and again we can try to explain this variation by including characteristics. It can be more complicated. For instance, well, in the data set that I discussed, some analysis were done using 4-level models. So we have schools, but in some of the schools, more than one class was studied. Within classes, you have multiple students, and students were repeatedly measured. So we have a 4-level structure. Okay, how does it look like? Well, this is a 3-level model. So compared to the 2-level model, we have an additional index, k, and so the coefficients at the first level can vary randomly over the second level units. Possibly we can explain part of the variance by including characteristics. And then these coefficients in turn can vary over third level units. So to summarize, why would we use multi-level models? First reason is a statistical reason. We take into account the nesting of units in higher level units. And so this makes sure that the type 1 error rate will not be exceeded. But there is also a conceptual reason. Of course, in this kind of data sets, it's interesting to study to what extent are there differences between schools or between classes, and where do these differences come from? Can we explain these differences by including school or class characteristics? This was my short introduction in multi-level analysis. Now, meta-analysis as a specific situation or a specific instance of a multi-level analysis. So in our example, we had 2 levels. We had students nested within schools. In fact, in the meta-analysis, we have a very similar structure. We have multiple studies. And within studies, we typically have multiple participants. And there can be variation between participants from the same study, but there can also be variation between studies. And it's interesting to study why there is variation. We can include study characteristics. We can include participant characteristics to try to explain this variation at the 2 levels. How does this multi-level model look like? Well, suppose you have a set of studies, and in each study you have a control group and an experimental group. Well, you could use this model, this equation, to describe the variation within the study. So it's a simple model. Our dependent variable is regressed on a treatment dummy variable to indicate whether this person is part of the treatment group rather than the control group. And so how do we have to interpret this? Well, so the beta 0, the intercept, is the expected value for somebody from the control group. Yeah? So it's the expected value or the population mean of the control condition in that study. The effect of treatment is what is added to this expected value if somebody belongs to the treatment group rather than to the control group. And so this coefficient refers to the mean difference, the population mean difference between these 2 conditions. So you see, it's a measure of effect. It's the effect of the treatment. So the effect of the treatment is expressed by this coefficient beta 1. And the variation, well, it's possible that the intercept, as well as the effect, the treatment effect, can vary over studies. And this variation can be described using additional equations. So the intercept is equal to a mean plus a random deviation, a random effect that is typical to that study. Same for the treatment effect. So the mean, here you have the mean treatment effect or the overall treatment effect. And this is a random residual specific to that study. Of course, it's also interesting to study the between study heterogeneity in treatment effects. This is expressed using this parameter. So the variance between studies in the treatment effect. So you can recognize the parameters that we typically estimate in a meta-analysis. To illustrate this, I simulated a small data set using this population model. So the mean intercept, so the overall expected value in the control condition is equal to 1. The overall treatment effect is equal to 1, but there is some variation between studies in both coefficients, and at the first level within studies, you have a residual variation of 1. I simulated data from 30 studies with each 2 groups of 30 units. I analyzed the data using a multi-level analysis, and so here are the parameter estimates. You can see that, well, these parameters are quite close to the population values, but of course, if I would have thrown another sample, would have simulated another data set, these values would have been slightly different, and then maybe now this value is slightly smaller, maybe by simulating another data set, that value would be larger than 1. Yeah? Of course, you could say, well, this is not a typical meta-analysis. In a typical meta-analysis, yeah, you have data from several studies, and in these different studies, typically outcome variable is not measured on exactly the same scale, so we have to standardize the data. Okay? One way of standardizing the data is by dividing the dependent variable by the standard deviation within the study. In fact, an estimate of this parameter is the pooled standard deviation, which is also used when we calculate a standardized mean difference. So in fact, the coefficient now, it was a mean difference. Now it is a standardized mean difference that you recognize from meta-analysis. I put here primes because the parameters, of course, change or can change. But otherwise, it remains the same model. You can use multi-level modeling software. So let's look again at a simulated data set. So now parameter estimates, or the population parameters remain exactly the same because already in the first data set, the variance within studies was 1. So standardizing doesn't make a difference here. But now in the simulated data set, I analyzed the data after standardizing the data within each study with an estimate of the within study residual standard deviation. And so you get similar results as the ones I've used before. In a real meta-analysis, of course, again, this is not a realistic situation because in a real meta-analysis, we typically do not have the data of each individual participant. Yeah? So such an ordinary multi-level analysis is not possible. So rather, instead of having the data from each individual participant, we have summary statistics about the sample of participants within each study. We might have test statistics, mean, standard deviations, and so on, or effect sizes. And yeah, we can use these effect sizes to perform a meta-analysis. Typically, for common effect sizes, we also know, or the sampling variance, or we can obtain good estimates of the sampling variance. So the sampling variance, or the variance at this first level, does not have to be estimated anymore. Sorry. So we only have to estimate the variance at the study level. But otherwise, we can use the same framework. Let's look at the model I showed before. So remember that this parameter is a standardized mean difference. So what if we have effect sizes? Well, a standardized mean difference that is estimated in a specific study, in fact, is an estimate of this beta 1 prime. So it's an estimate of the population effect size. Of course, it's possible that the estimate is slightly too high or too low, so there is a residual. And the residual, we assume that these residuals follow a normal distribution with a variance that we do not have to estimate anymore. We already know that variance. At the second level, so here, this equation remains the same equation. Yeah? So the population effect size is equal to a mean effect size plus a random residual typical to that study. Let's look at the results of the simulated data set. So in the simulated data set, I calculated observed effect sizes or standardized mean differences for each of the individual studies, and I analyzed them using such a multi-level model for effect sizes. And look at the values. You get exactly the same values for the mean effect as well as for the variance between studies in the effect. So this is just to show that effect sizes in this situation are sufficient. We do not need more information than the information we have with these effect sizes. Now, why would we use a multi-level model for analyzing or meta-analyzing data? Well, first I'm going to talk about the meta-analysis of raw data. You can say, well, typically we do not have raw data, but sometimes we do. And to illustrate this, I will discuss a reanalysis of a meta-analysis that was done by Carrie Shockley. She did a meta-analysis on several single case studies that studied the effect of choice making. She looked at studies that investigated whether problem behavior of students in classes can be reduced by giving these students a choice in the activities or in the order of the activities. And so she found several studies single case studies, and single case studies are experimental studies in which individual participants are measured repeatedly over time under different conditions. So here, without having the choice and with having the choice. Here are the data for one single participant from one of the studies. And so, for instance, well, this is a typical way in which the data are presented in single case studies. So they are typically presented visually, graphically, and they are typically also analyzed visually, so without statistical analysis. But the nice thing about this tradition is that from these graphs, we can retrieve the raw data. And so we can use multi-level models to analyze these data or to meta-analyze the data over several studies. So what do you see here? Well, first, that person was measured during 8 sessions without having the choice. You can see that the problem behavior is relatively large. So this is a percentage of intervals in which there was problem behavior. In a second phase, there were sessions in which the students could choose the activities or the order of activities. And then you can see that the problem behavior was reduced. It's much lower. Then in the third phase, again, they did not have the choice. Again, problem behavior is larger. Then in the fourth phase, again, there was no choice, or they could choose again. And so you can see that the problem behavior was reduced again. So looking at this graph, you can see that at least for this participant, there seems to be an effect of giving choice. But we had data, or Gary Sjogren collected data from several studies. And in some of these studies, 2, 3, 4 cases or participants were studied. So we had a lot of these time series graphs. And so we have analyzed this data using this model. So at the first level, we say, well, the score is equal to an expected score in the baseline phase, so without having the choice. But something is added, and here something negatively is added, if people are getting the choice. So problem behavior here is reduced. So beta 1 is the size of the effect for this participant of having the choice. In the data set, we had 13 single case studies, in total data from 30 cases. So we used the 3-level model to study variation between measurement occasions within cases. And of course, we took into account whether at that moment they had a choice or not. There can be variation between cases, there can be variation between studies, and we can try to explain this variation by including case and study characteristics. So we use this model, 3-level model. Here are the results. So on average, the intercept, after standardizing the data for each study separately or for each case separately, so on average, the amount of problem behavior in the control condition was 3.07, but you can see that the amount of problem behavior was reduced. It was more than 50% reduced by giving the students choice. We can include characteristics of studies, characteristics of cases as moderator variables, or as predictors in the second and the third level equations. So at the second level, we included the gender of the person. At the third level, we included, well, there were 2 types of studies. In some studies, the students could choose the activities. In other studies, the students could choose only the order of activities. So we included here a predictor, a dummy variable indicating whether they could choose the order rather than the activities themselves. And so, here are the results. So if you are talking about a female and if they could choose the activities themselves, then the reduction of problem behavior was minus 2.86. But if it was a male, then the reduction was somewhat smaller. If they only could choose the order, then the reduction was even smaller. Okay? So that's the meaning of these coefficients. What is nice about the use of multi-level models is that multi-level models are very flexible. So you can extend this simple model in several ways. For instance, you can include or you can model autocorrelation, you can model heterogeneity, so you do not have to assume that the variance within the baseline phases, for instance, is the same as the variance within treatment phases. You can also include additional covariates at the first level. For instance, if you have 2 treatments, you can use 2 dummy variables for the 2 treatments. You can, if you have count data, you can use a generalized multilevel model rather than an ordinary multilevel model. You can also include linear and non-linear trends over time at the first level, and so on. So a lot of extensions are possible. So for instance here, this is a model that can be used to model a time trend in the baseline phase, a time trend in the treatment phase, and in this model we have 2 effect sizes. In fact, beta 2 here refers to the immediate effect, whereas beta 3 refers to the interaction effect. So the effect of the treatment on the slope over time. So you can see it's a very flexible model. What about the multi-level meta-analysis of effect sizes? So this is the typical structure for each, this is the structure that is assumed when using traditional meta-analytic techniques. So we assume that for each study we have 1 sample of participants, and so for each sample we only have 1 effect size. So theta here refers to the population effect size, t to an observed effect size. So these observed effect sizes can be assumed independent. But sometimes, well, there can be various reasons why effect sizes might be dependent. For instance, it's possible that there are dependencies over studies. For instance, maybe some studies were done in Belgium, some in Germany, some in the United States, and so on. Suppose that these are studies done in education. Well, the educational system is completely different in the United States compared to Germany. So you can expect that the results of studies done within the United States are more similar than results of studies done in Germany. So again, there is overlap in information, and it's important to take that overlap into account, otherwise your type 1 error rate will be too high. So we could use a 3-level model. We can extend the 2-level model that I showed before by including an additional, higher level. It's also possible that you have dependencies within studies. So for instance, sometimes you have studies, and within studies, several experiments are done. And so again, it can be interesting to study to what extent there are differences between studies, but also to study to what extent there are differences within studies, between these sub-studies or experiments within studies. And in the next step, we can try to explain this variation by including study characteristics or by including characteristics of these sub-studies. For instance, what subpopulation was studied in this sub-study, or what variation in the treatment was evaluated, and so on. This is a model so again, we can use a 3-level model. So we have at the first level, we have our sample level, so with the sampling variance. At the second level, we have the level of sub-studies with variation between, possibly variation between sub-studies. And at the third level, we have the studies. This is the model we used for our meta-analysis on priming effect studies. And we found that in a lot of studies, several experiments were done. Typically, these experiments were replicated in different groups, but with a slight variation in the way the treatment was operationalized. Yeah? And so by calculating a simple average within each study, you would lose that information. Yeah? Whereas when using a 3-level analysis, you still keep that variation between sub-studies within studies, and you can try to explain this variation by looking at for instance, the time the prime was offered, does it have an influence on the size of the effect? So in the first step, we did random effects model analysis, but a 3-level random effects model. So we found that at the 3 levels, we had more or less the same amount of variation. And then we did moderator analysis, and we found that with only one moderator variable, one study characteristic, and one moderator variable at the second level, so one characteristic of the experiments within studies, we could explain a large part of the variation, especially the variation at the third level, so the variation between studies. You see that only a small part was left. So you could call this a mixed effects model, because it includes moderator variables, but still accounts for possible remaining unexplained variance at the 3 levels. It becomes somewhat more complicated in a very common situation where within a study you have one sample, but within that sample multiple outcome variables were measured. And this is more complicated because in a typical meta-analysis we assume that we know the sampling variance, but here we do not only have sampling variance, we also have sampling covariance. Suppose that you have two kinds of outcomes. You have depression and anxiety that are two variables that are strongly related. Suppose that in one specific study, the effect on both variables is evaluated. Well, if in a study, by coincidence, that effect size for anxiety is relatively low, well, you would expect for that study that also the effect size for depression will be high. So you can expect that there is not only sampling variance, but also sampling covariance. Well, I guess most of you are familiar with the formula for calculating the sampling variance. This is the formula for calculating the sampling covariance for standardized mean differences. And note that the sampling covariance depends on rho. Rho is the correlation between the outcome variables. And this is a problem. We typically do not know this correlation. And very often this correlation is not reported. So how can we take that covariance into account in our meta-analysis? Well, maybe one solution is to use a 3-level model. Again, with the structure I showed before. So we have studies. Within studies now we have multiple outcomes. And for each outcome we have a sample. In fact, this is not the correct structure. Here, I say, well, we have different outcomes, but for each outcome we have one sample. So we ignore the sampling covariance if we use this structure in our meta-analysis. Yeah? But maybe this covariance, this dependence is taken into account by saying, well, yes, these two outcomes belong to the same study. Okay, so that's the idea. This is the model we use, for instance, in a meta-analysis on 39 studies, reporting on 584 effect sizes. In each of these studies, the effect was evaluated of prevention programs for child abuse and neglect. So why do we have that many effect sizes? This is because child abuse and neglect is very hard to measure. If you ask to parents, how many times did you beat your children this week? Of course, I will say 0. So it's very hard to measure. And so there is, you can also not observe it. If researchers would make observations at home, of course, parents will not abuse or neglect their children during the observations. So that's why in a lot of studies, researchers were very creative in finding ways of getting an idea of where there is child abuse or neglect. And so in some studies, they looked at reports done by teachers or by supporting services, but also sometimes they looked at the number of visits to emergency rooms or a number of visits to a doctor, or sometimes they even simply looked at risk factors like the number of friends of the family or the income of the family or things like that. Yeah? And in some studies we only found one effect size, but in one study we found up to 51 effect sizes. Yeah? So we had a lot of effect sizes. We did a 3-level analysis and we found, well, on average, so we calculated standardized mean differences. So on average we found a relatively small effect, but it was clearly significant. Between parentheses you have the standard error. Here you can see the variances between studies, between outcomes within studies, and this is the median sampling variance. So in total, if you sum these 3 values, you have the total variance. And so you can see that about 11% of the variance. So this is comparable to what Mike showed. So the values I squared at the 3rd level or at the 2nd level. So about 11% of the total variance is variance between studies. About 33% of the variance was variance between outcomes within studies. And so, of course, we try to explain these variances by including characteristics, for instance, the type of indicator variable, or that's a variable a moderator variable at the second level, or for instance, the prevention program that was evaluated, and it was a characteristic of the study. But is this a good idea? Because I said it's not a correct model. We ignore the sampling covariance, and we hope that it is accounted for by using such a tree-level model. So what we did, we performed several simulation studies, for instance here, using this multivariate model. So we simulated data for 2 outcome variables that possibly can co-vary within studies, but these 2 outcome variables possibly can also co-vary at the second level over studies. And so we analyzed, or we generated raw data, but we calculated effect sizes, standardized mean differences, and we analyzed them using a tree-level meta-analytic model. And so here are some results. So these are the standard deviations for specific conditions, standard deviations of the mean effect estimate. And you see that the standard deviation is going up if there is more covariance, which is what you would expect. If there is more covariance, then this means that the outcome variables overlap more. There is more overlap, so the estimates are less precise. They vary much more. Okay? So you can see that the standard deviation of the estimates are going up. And you see that there is no difference between using a 3-level model or a 2-level model. Yeah? In fact, we found that estimates were almost exactly equal when using the 2 models. But here, we also looked at the median or the mean standard error. What you can see here, if you use a 3-level model, the standard error is also going up together with the sampling variance. Note that the standard error of the estimate is an estimate of the standard deviation of the sampling distribution of the mean effect. Yeah? So you would expect, or you hope, that the standard errors are very similar to the standard deviations here. And this is the case for the 3-level model. For a 2-level model, you see the 2-level model does not take into account the sampling covariance. So a traditional model, using a traditional model is not a good idea. The standard error remains the same, and as a result, you can see that the type 1 error rate is not under control when using a 2-level model. But for a 3-level model, it is nicely under control. We tested here with a significance level of 0.05, and the type 1 error rate indeed for a 3-level model is 0.05. So the type 1 error rate is under control. What is also nice is that we now have an estimate of the variance between studies and within studies. We can also try to explain these 2 variances. So I think you can solve interesting questions by using such a 3-level model. Of course, the drawback is that it's not that very well known. Also, some software like Refman or CMA does not allow for doing 3-level analysis. We also make some assumptions. For instance, we implicitly assume that the correlation between each pair of outcomes is the same, or we assume that the between-study variance is the same for each outcome. But we also did additional simulation studies varying these variances and correlations, and we found that results are fairly robust. What are alternatives? Well, ignoring the dependence is not a good idea, as we have seen. Type 1 error rate is not under control. An alternative is randomly choosing one effect size for each study, which was already mentioned this morning by Mike. Or it's statistically correct, because in this way, you only have one effect size per study, so effect sizes are independent. But you, of course, you lose information. You do not use all effect sizes, and moreover, you do not get an insight in how many variation is there within studies. And can we explain this variation? Averaging effect sizes within a study, same problem. So you lose information. Moreover, if you want to use the sampling variance in your meta-analysis, well, the sampling variance of that mean depends also on the correlation between the outcomes. So again, we have the same problem. And what is typically done is also the sampling variance is averaged within the study. But that's not a good idea, because the more outcomes or the more effect sizes within a study you combine, the more precise the result is. Yeah? So you should take that into account in your sampling variance. The problem is how, if you do not know what the correlation is between outcomes. It's also possible to perform separate meta-analysis for each kind of treatment or indicator. But of course, again, for each of these separate meta-analysis, you only use part of the data, so it's not a very efficient way. Moreover, think about that example that I gave of child abuse. In one of the studies, you had 51 outcome variables. So are you going to do 51 meta-analysis? So this is not realistic. Performing a multivariate meta-analysis, that's statistically okay, but again, you have some problems. Often, well, if you want to do a multivariate meta-analysis, typically you are also going to use an estimate of the correlation between outcomes, which is typically not reported. And it's only feasible if you have a limited set of outcome variables. Again, think back of that example of child abuse. If you have 51 variables in one study, you cannot expect that for each pair of outcomes you have a good estimate of the correlation between these outcomes. Another alternative is robust variance estimation. So in fact, in this procedure, you are estimating a two-level model, so a misspecified model, in fact. But by using robust techniques, you make sure that the standard error is still okay. And indeed, it has been demonstrated, well, mathematically, but also via simulation, that it gives correct standard errors, that the results are fine. I think also an advantage of this approach is that you can use a standard two-level model, which is much better known by a lot of people. So you will not have such a hard job to explain why you are using three levels. But I think a disadvantage is that you do not get separate estimates of the variance between studies and the variance within studies. Of course, it's possible, related to your remark this morning, it's possible to extend this even more to additional levels. It's possible to do a 4 or 5 level analysis, for instance. So here, for instance, you have a level of an additional upper level of the studies, and within studies, you have a level of sub-studies. In principle, that's possible, but it's not very common. Another kind of model that was described by Belén Fernández Castilla, one of the PhD students in our group, is a cross-classified model. So here we say, well, we illustrated this also using a data set on loneliness outcome variables. But we assumed, well, we can have variance between studies in the size of the effect, but there can be also variance between the instruments that can be used. And this model is more complicated, or the structure is more complicated in the sense that it is a non-hierarchical structure. So instruments are not nested within studies. So the same instrument can be used in several studies. At the same time, studies are not nested within instruments. So the same study can use multiple instruments, like this study. Yeah, so we have a cross-classification. A population effect size is a population effect size for this study when this study uses this instrument. So there are two effects, two random effects. And again, we can include characteristics of the instruments or characteristics of the studies. Very shortly, something about the use of multi-level meta-analysis. When is it used? Well, I did a very quick search in the Web of Science. Using these keywords in the topics, I found 90 studies. And what is remarkable is that the first study that I found was from 1996, whereas, of course, this is not a complete overview, and there are much more studies, but this gives already a quick idea. So although the fact that that the use of multi-levels for meta-analysis was already described, for instance, in the book of Raudenbusch and Brick in 1992, you see that it was hardly used until the 2010s. Yeah, and now you can see that it's getting much more popular. So this is a nice finding, an interesting finding. Also the number of citations. These kinds of studies were hardly cited until 2010. In what domains were these studies published? Well, typically in psychology, behavioral sciences, which is also interesting. I don't know how to explain this, but it's a finding. We also looked at what applied multi-level meta-analytic papers referred to these three papers. So a paper of Mike and two papers of our research group on three-level or multi-level meta-analysis. And we found that 104 studies referred to these papers and indeed used multi-level models. An interesting finding was that 99 of these studies used a three-level model with an intermediate level. So with a study level at the highest level and then the within study level at the second level. Two of the studies also used a three-level model, but with an additional level. So for instance, so we had the sample level, we had papers level, and then we had the studies level. So the same studies, it was, I think it was also mentioned by you this morning, so maybe the same data set is used in different papers. So this is the situation. So we did not find here a study with countries or research teams at the highest level. There were only 3 levels that used a 4-level model, with samples, outcomes, studies, countries, sample outcomes, sub-study studies, or sample subtasks, tasks as studies. Again, we found that most of these studies were in the psychological field. One other PhD student of our group, Lala Yamshidi, made a review of meta-analysis of single case studies, and she found that between 1985 and 2015, 178 meta-analyses were done on single case studies. And 22 of these studies used multi-level models. It was striking that most of these, almost all of them, are also published after 2011. So you can see that the use of multi-level models is becoming much more popular. A few more words, if I have the time, on how to present the data or the results. Well, of course, if you take into account each individual effect size within studies, you can have a lot of effect sizes. So how are you going to present this? Well, this is a way of presenting this. So here you have one confidence interval for each observed effect size, but it does not give a clear overview. Moreover, you cannot see what effect sizes are nested in what studies. Okay? You could, of course, use different colors, but if you have a lot of studies, then the use of colors or different markers also does not give a good overview. So now we are exploring ways of giving better presentations of the data, and this is a possibility. So Belen is describing several ways of presenting the data, and so this is one way. So here we have a dot for each study. In fact, the dot represents the mean effect for that study. And around that dot, and the size of the dot represents the weight that is given to that study in the 3-level meta-analysis. And around that dot, you have 2 confidence intervals. So the bold confidence interval refers to the precision of that mean of that study. Okay? Whereas the lighter confidence interval refers to the median, or refers to the confidence interval based on the median sampling variance of an individual effect size within that study. So for instance here, if you look at study 5, you see that the black or the bold confidence interval is much smaller than the light one. This is because you had a lot of effect sizes. So therefore the mean effect size is much more precise than an individual effect size. Whereas for study 7, you have 1 effect size within that study, and therefore the 2 confidence intervals are exactly the same. So that's one way of presenting. What can also be interesting is to make a caterpillar plot. So of all observed effect sizes, individual effect sizes. So here you can immediately see that the majority of effect sizes are positive. A lot are also 0, and some are negative. It's also possible to make a caterpillar plot over studies, or on the mean effect sizes for the individual studies. Again, using these 2 kinds of confidence intervals. So maybe this is also a way of presenting the data, but as I said, we are simply exploring possibilities, so if you have better suggestions, I'm very curious to hear them. About funnel plots, well, we can make a funnel plot for the individual effect sizes, but we can append this information by making a funnel plot with the mean effect sizes for these studies. So here, each dot refers to the mean effect size for one study. Maybe we can also add the number of observed effect sizes within each study as additional information. Okay, thank you.
Thank you very much for a very interesting talk. I was wondering, I like the pictures that you showed in the end. So did you make a package or R functions that we can use to immediately create those pictures for our own data?
It's the purpose, yes, to make R scripts that can be used. We will make them available using our website. Yeah.
Yeah, thanks.
Thanks, it's very nice. And I'm interested in various combinations. For example, there are three-level meta-analysis, cross-classified with for some of these meta-analysis, maybe there are two dependent variables or more. So do you think it is possible to write some general or easy code, let's say R packages for somebody to analyze? Because it looks like nowadays for each problem we have to write a single R code or to customize, to analyze the models. So I understand you're using SAS, right? Or other packages?
Yes, I'm using mostly SAS. Yeah.
So,
and there it's easy to say what the random effects are.
Yeah.
So what effects vary randomly over what units?
Yeah, so I'm thinking whether it will be some user-friendly, either SAS, macro, or R, so that they can easily mix and match. One of the issues I always have is they have multiple effect sizes, but they have also dependence. So there should be something similar to multivariate three-level meta-analysis. Then you always have struggle how to analyze it. We all know there are methods, but how to implement it is an issue.
Yes, that's a very good point. Yeah. Yeah, we are aware of that. We are not really planning to write an additional package, but we hope that maybe in existing packages, extensions can be made to model this kind of, or to analyze data using these models. But we certainly will also make available the codes that we use in SAS or in R. Yeah. Thank you.
Thanks, nice presentation. Did you compare the results of the cross-classified multi-level meta-analysis to a standard meta-analysis, and what are the differences? So what is the benefit of estimating these more complicated models?
Comparing the cross-classified?
Yeah, to the standard meta-analysis. To the standard,
yes.
Yes. More
yeah,
level
we did a simulation study. Comparing the results of using this model with a model in which you include only one type of random effect, so the random effect for the studies or the random effect of the instruments. We also compared it to the analysis of the data using a three-level model, where you have, a three-level model, but with, I have to think. We had random effects within studies, so it was not exactly the same structure as I showed here. So we had, within studies, we had two kinds of random effects in our simulation study. And we also analyzed the data using a three-level model, in which we looked at, can we solve this by taking a combination of these two crossed factors? And so we found that the best solution or the best performance was for the model that indeed took into account the cross-classification structure. And so the results are, as expected from other simulation studies, that the type 1 error rate was not under control when using other models.
Thank you for the great talk. I was wondering, can you say something about the minimum number of sampling units that is needed on level 2 and level 3? Because sometimes we have meta-analysis with a relatively low number of studies, or if you want to compare countries, you only have a low number of countries. And how important is it that you get a certain minimum amount, or if you're under the minimum level, is that a huge problem?
Yeah, thank you. That's of course a very important question, and it is an issue. It is sometimes an issue. So first of all, for the fixed effect estimates, it does not matter. I mean, we found in a lot of simulation studies that fixed effects are well estimated, even if you have small numbers of units, even if the model is not correct. Like in the simulation study I showed before, whether you use a 2-level model or a 3-level model, fixed effects estimates are almost identical. So that's not a problem, but for the standard errors, it's important that you use the correct model, and you should indeed have enough units, at least at the highest level. So it's not a problem if within studies, for instance, you only have for some studies 1 effect size, for other studies 2 or 3 effect sizes, that's fine. It's especially important that at the highest level you have enough units. And what is enough? Well, yeah, in multi-level analysis in general, sometimes as a rule of thumb, they say you need at least 20 or 30 units. Now, we have done a lot of simulation studies, and sometimes we found that with much smaller numbers of units, you still get correct results. Type 1 error rate is still under control, at least if you do not have moderator variables in your model, if you simply estimate the mean effect. So sometimes with 10 or even with 5 studies, you get reasonable good estimates of the standard errors and therefore correct coverage proportions of confidence intervals and so on. Of course, if you want to study moderator effects, and also if you want to make inferences on the variances, then you need more studies. So for instance, in the simulation study of José Antonio López from the University of Murcia, well, he found that if you want to include moderators at the 3rd level, so at the study level, you need at least 20 studies. Otherwise, your type 1 error rate is too high. By the way, when you use the RVE approach, or the robust variance estimation procedure, type 1 error rate is still under control if you use somewhat smaller numbers, although the procedure is somewhat conservative. Okay? Yeah, maybe one additional remark, of course, there is also the issue of power. So even if with 5 studies or with 10 studies, results might be okay, the power will be very low.
Hi, thank you. It's very interesting. I think there is a lot of possible examples where you could imagine this would be useful. So I was thinking of, for example, also subgroup analysis and meta-analysis. So you have subgroups within the studies, and you mentioned this, right? You could say that within the same sample they have shared variance. So do you have some rule of thumb, maybe, like there's out there for other types of analysis, when to include a level in your analysis, maybe compare it and then, or leave it out to simplify it a little?
Yes, that's a hard question. But of course, again, yeah, a very interesting and important question. So what I did not really mention is that implicitly we assume, when we use random effects, we assume that the units that we have are a random sample out of an infinite population. So for instance, I give the example of instruments. So yeah, this was also a remark we got from a reviewer. Yeah, there are not an infinite number of instruments available to measure loneliness. So that's one issue. So do you want to say something about individual instruments? And then it's not a good idea to use a level or use random effects for the instrument. Then you can include the instrument in your analysis as a moderator. You can use dummy variables for the different instruments, and then you get an estimate for each instrument. You can. So that's one thing. Second thing is, yeah, if we want to generalize to instruments in general, what are instruments in general? Can we assume that there is such a population of instruments? And also, we made the assumption that these random effects are normally distributed. So why, is it reasonable to assume that these random effects are normally distributed over instruments?
So does it mean you would say that to purely think theoretical and not look at how much variance is explained on that level at all?
Okay, yeah, so that's indeed another issue. So, yeah, sometimes it's from a theoretical point of view, it can be a good idea to use a 4 or a 5th level. But it's possible that the variance at an additional level will be very small. And so in that situation, it's not such a problem if you ignore that level. Yeah, the results will be very similar. And that makes also that it's easier to interpret your data, that it's easier to communicate about your results. So it's always a trade-off. How complicated do I want to make this model? You also do not want to over-specify your model. You also do not want to catch the peculiarities, the random errors in your data set. So it's finding a matter of finding a balance of estimating a reasonable, realistic model on one hand, but not making it too complex on the other hand. Thank you. Thank you very much. Once again,